Alright guys, welcome to the next lesson of our networks unit. In this chapter, we'll be covering 9F and 9G. So Eulerian trails and circuits. Remember last lesson, there are a few terms or new words that we learnt when it comes to networks. Okay, we learnt about trails and walks, okay, and paths and circuits. These sort of words you need to make sure you understand, because it's hard to be able to do these questions if you don't get this. So make sure you watch this video so you understand what the 4 new words are. Actually, there's 5. You can condense it in this table here. A walk, a trail, a path, a circuit, and a cycle. Okay, those are 5 sort of new things we learned about. Closed walk, I've not included really because they kind of relate to what a walk is, but basically, a walk is if you have a network, okay, and you're able to go anywhere with no rules. Trail is when you go to anywhere on the graph, but you just can't repeat an edge. Okay, you can't go back to an edge. A path is when you can't go to anywhere in the graph, but you can't repeat an edge or a vertex. Okay. Closed walk means you start and finish at the same spot, so you can go anywhere. No rules, but start and finish at the same spot. A closed trail is what we call a circuit. So remember, a trail is you can't repeat any edge. So if you you can't repeat any edge, and you need to start and finish at the same spot or the same vertex. A closed path is basically a cycle where you can start somewhere, but you can't repeat any of the vertices except for the start and finish. Okay, so that's what we learned about in the previous video. So make sure you watch that in order to get this one. Now here we're going to be talking about Eulerian trails and circuits. So remember, a trail or a circuit, okay, depending on what you're looking for here, a trail or a circuit, okay, includes every edge on the graph. But this only works if it's a Eulerian. Some teachers might say Eulerian, but I say Eulerian. So Eulerian trail or circuit has every edge. So you're going through every single line or edge in the graph. So you can't skip any. Okay. Since a trail or circuit is a walk with no repeated edges, a Eulerian trail or circuit is a walk that includes every edge on the graph exactly once. Okay. So when we're saying every edge, it's only once. So you can only go through every single edge or line only once. Okay, now you might be wondering, why do we call it a trail or a circuit? Why can't you just call it one or the other? Well, there are certain rules when it comes to it being either a Eulerian trail or a Eulerian circuit. Okay, and we'll get to that in a second. But basically, a graph is traversable, so you'll see this word being used. Traversable means you can go through every single edge once. Okay, every single edge once, exactly once only, no repeats. Okay, and it's either a trail or a circuit. So here we're going to look for specifically Eulerian trails. Okay, so a Eulerian trail, this is just for Eulerian trail. Okay, it means you can go through every edge. Shall I put that here? Every edge once. Okay, edge once. But the only rule here is the start and finish is different. Okay, when I say start and finish, I'm meaning the start and finish vertex is different. Oops. So you might start at one vertex, but you end up at a different one. So that's what a Eulerian trail means. Every edge once only, but the start and end, okay, is going to be different. I'll highlight that. So for a Eulerian trail, okay, Eulerian trail, every edge once only, but the start and end is different. So let's try it here, this graph. So here I can see, okay, that I've got obviously 4 vertices. Let me just close that. 4 vertices. Okay, and we're going to try and go through each and every single edge once only. So I might start at A. Let's go A to B, down to C. Might go back up to B. Then I could go to D, then C, back up to A, and then D. So what I've done here, okay, is remember you can go, when it comes to a Eulerian trail or circuit, you can actually go to the other vertices more than once. Okay, that's fine. The only rule is you have to cross through every single edge once only. So for a Eulerian trail, remember, I can start and finish anywhere. Okay, every edge once, but I have to start and finish, or I can only start and finish at different vertices. So if I started at A and I went to B, so I can go A to B, down to C, then up to B again. So C, then B. And up here, then I can go down to D, then to C, C, and then up to A. Excuse the horrible drawing. And then down to D. And notice how I've gone through every single edge, but my start and my finish are different. Okay, that's what you call a Eulerian trail. Let's try another one here. Eulerian trail. Start and finish different spots. Okay, so this one's going to be a bit tricky. Let's see if we can do it. So I can go from A to B to C. Then I can go down to F and B. I can go to E, F, D, E, D, C. Okay, notice how I've gone through every single edge once only, but my start and finish were different. So let's draw out my path. So on my the path that I took. So A to B is the first one. Then I went down to F. Did I do that? No, actually, so C. C, my bad. I went up to C. A, B to C. Then I went down to F. And then to B. And then all the way down to E. Up to F. And up to D. Down to E. Up back to D. And then finishing off at C. What you'll find as well, guys, is there actually may be more than one of these solutions. Okay, so the interesting thing with networks is there's not always just one answer. You might have more than one answer with this. Okay, but what you'll find here is that I started at A and I finished at C. So the start and the finish are different. That's with Eulerian trail. Now with Eulerian circuit, these are slightly different in that what's different here is that for your circuits, okay, every edge once again, okay, once, but the start and finish is the same. Okay, so the start and finishing vertex is going to be the same. So for Eulerian circuit, okay, that's what it is. That's what the definition is for this one. Again, every edge once only, but the start and finish are going to be the same vertex. All right, and we'll see how this works out. Let's see. All right, so for this one, I might start at A, and then I'll go up to B, E, I can go to C, D, F, E, A, can go around to C, go back to F, and then finish up at A again. Okay, so I've gone through every single edge there. Let's list out my path. So I started at A, then I went to B, E, C. So I went to B, to E, then went to C. Then I can go down to D, then to F, A, E, then A. F, E, to A. Oops. And then I went all the way around to C, go down from C to F, and then finishing off at A. Notice how my start and finish were at the same spot. Okay, A and A, right at the same spot. So that's a Eulerian circuit. With the Eulerian circuit, you can start and finish at the same spots. Okay, let's try. I'm going to minimize this a bit. Let's try this graph here. So can we find a Eulerian circuit here? Okay, so I'm going to start by drawing it. First I can go A to B to C, then C to B, back to A, and then go around over to C, and then back to A. So my start and finish were the same there. So let's try that. So you've got A, so let's not try that, let's write that. B to C. Again, you could have multiple answers for this, okay? So totally fine if your answer isn't the same as mine. However, the only thing is you need to make sure you stick to the rules. Okay, you got to make sure you go through every single edge once only. And if it's going to be a circuit, start and finish must be the same. Okay, you can go, this middle bit can be different. You could have gone, if you wanted to, you could have gone A to C, then back to A, then go B, C, and go back to B, then back to A. See, it gives you the same result. All that matters, okay, is that you start and finish at the same vertex, and that you go through every single edge once. That is for a Eulerian circuit. All right, so how do we know? So without having to work it out by hand, how can we tell if something is a trail or a circuit for a Eulerian? So this is the shortcut that I'm going to be showing you. So if you want to figure out if something is a trail, a graph that contains a Eulerian trail includes exactly two odd vertices. So two vertices on that graph are going to be odd. So if you've forgotten how to determine this, go back and watch chapter 9b and c, I think. Okay, but how do you figure out if the vertices are odd? Okay, so if you're looking at a vertex, just look at the number of connections to that vertex. That'll tell you whether it's odd or even. So these are all even, okay, because you can see that that's got 4 lines joining to it, 4 lines joining to that, 4 lines to that. Okay, same with this, all of them are even. But these guys are not all, 2 of them are going to be odd. And I can see that A and D have an odd degree, okay, because it's got 3 lines connecting to both of them. All right, so if it's got an odd degree, that means it's going to be a Eulerian trail. Or two odd vertices, it's a Eulerian trail. I'll also say even if one has a prime number, so if it's just 1, that'll also work. This has only 1 degree, so that would be counted as having an odd vertex. So it has to have exactly 2 odd vertices for there to be a Eulerian trail only. Okay, for there to be a Eulerian trail. And the cool thing is, when you find those 2 odd vertices, the trail begins and ends at these 2 vertices. It has to start and finish there. Notice how when I did these, I started at A and I finished at D. I knew that that was going to be the case because they're both the odd vertices. Here again, I started at A, I finished at C because I knew they'll be odd. Also, I could have started at C and finished at A. That would work as well. Okay, but you have to start and end for a Eulerian trail at start and end at the odd vertex. For a Eulerian circuit, so this is where it's slightly different, a Eulerian circuit, every vertex must be even. So I'll know if there is a circuit, a Eulerian circuit in there, when all of the vertices are even, all of them. Okay, and for this, the cool thing is you can start and end at any vertex, doesn't matter. As long as, again, you've gone through every single edge. Beginning. So just keep that in mind, okay? Beginning and end can be anywhere for a Eulerian circuit, but for a Eulerian trail, beginning and end are different, and it's going to be at the odd vertices. You have to have exactly 2 for Eulerian trail, but for Eulerian circuit, everything is even. Okay, so let's see if we can find Eulerian trails or Eulerian circuits here without even having to go through it. Okay, so remember, for a trail, all of the vertices, so you've got to have 2 odd vertices. So here I can see the degree of this is going to be 3. Oops, 3. Okay, because there's 3 lines joining to it. The degree for this should be 3. This one will also be 3, and this one will be 3. Okay, now, because they're all odd, what happens is no trail, no Eulerian trail, no Eulerian circuit, okay? Because it's all odd. Okay, you can't actually go through and every single edge once only, no matter how much you try. Look, and I'll show you. Oops. I'll show you that. Sorry guys, computer's gone crazy. Okay, so if I start here, you can go through and try every single edge. Okay, but then I'm stuck here. I can't go back to that one. You can try from the middle. There, but I can't get back to that one. Okay, so because they're all odd, it's not going to work. So here, let's try this one. Okay, let's list out all the degrees for this. So that's 4, that's 4, that's 2, that's 3, that's 3, and that's 2. So because 2 of them are odd, that means only a Eulerian trail exists. Okay, so Eulerian trail here would exist. Okay, and you can find out what it is. But remember, for a trail, you got to start and finish at the odd vertices. So this is the start. Let's go from there. I can go here. I can go there. There you go. I found it. Okay, last one. Again, list out whether they're odd or even. So that's 2, that's 2, 2. That's got 4, and that's got 2. So that means this is all even. That means I can start and finish anywhere, and there should be a Eulerian circuit. And because of that, because a Eulerian circuit exists, a trail should also exist. Okay. Okay. A Eulerian trail should also exist. So say for example, I want to start. Let's see if this works. I'll start here. 1, 2, 3, 5, 6. Oh, yeah. So that would be a Eulerian. Yeah. Technically, you should be able to find maybe a trail. Not in all of them, but in some graphs, you should be able to find a trail. But technically, because this will be a circuit, you would say that it is specifically just a Eulerian circuit because all of the vertices are even. So I can go there. Remember, for Eulerian circuit, start and finish at the same vertex. Alright, and that's basically it for chapter 9F and 9G. So go ahead and do the exercises for it. Thank you.